It doesn't seem that long ago when I was sitting in this room in those chairs. Actually, not those chairs. Those are new chairs and new carpet. But that's the only thing. I don't think it's new paint. And that was a long time ago. It was the same room. So I'm very pleased to be back with you. It does feel like home. And let's see. So when does the bell ring here?
So, 10 till.
10-2. Great.
10 till.
Great.
You need a laser pointer for that?
I got one. I'll just bring it up. I forgot to bring it up. Yeah, so ask questions as we go. We'll see. I hope I pitched this at the right level so that you can understand what I'm talking about. If I haven't, then tell me, change gears, and we'll do that. So let's just talk. We'll turn the batteries the right way around. And nothing like that. We'll just let it work. Okay. Combustion simulations and kind of how they can be predictive. That's what I'm going to talk about. And I just want to talk about 3 examples. The 3 examples, we actually created a little spin-off company that's taking this kind of technology and helping use it in industry. And we say, and that's CRSim, we say that for combustion reaction simulations, we say that we do boilers, furnaces, and flares. So I'm going to give you one example from each. A boiler, a furnace, and a flare. Okay? And I think I'm going to go around it in a different order. I think I'm going to start with the boiler first. And then I'm going to talk about the furnace, the flare, and then I'll talk about this furnace or this burner. And we'll see where it goes. So the first is a project that is a project that's just beginning. This is a brand new project for us at the University of Utah in our institute, Institute for Clean and Secure Energy. We've been working with Alstom in the past. Alstom is a large boiler company. They build boilers around the world. This is a pilot scale boiler for them so that you can understand what the pilot scale is. You can see that 3 or 4 stories tall. And we're funded in this program from the National Nuclear Security Administration. It's a division of the Department of Energy. And they have funded this center that is going to begin financially about the 1st of March. It will go for 10 years, actually. It'll go for 5 years guaranteed, and then if we do okay, they'll renew it for another 5 years. And we're spending $5 million a year on this research for the next 10 years. Most of the faculty are from the University of Utah, and then we've got a number of people from Alstom, as I mentioned, who are participating with us. They don't get any money. They're just working, using their own money to pay for their salaries, and doing and then bringing experimental data to the table. And then we have 2 faculty members that are working with us at Berkeley. Professor Fletcher mentioned that one already, and 1 very prestigious faculty member from Brigham Young University that did the introduction. And so we're very happy to be working together on this program. What we're working on is using big computers, the biggest computers in the world, high-performance computers, extreme computing. I'm going to tell you a little bit more what I mean by that, to see if we can use big computers to have an impact on the world. And the impact that we have chosen and that they funded was to do the design of a high-efficiency, advanced, ultra-supercritical, oxy-cold, tangentially fired power boiler. That's a mouthful. I'll describe what that means in a moment. The goal is to do extreme computing, particularly computing at the exa scale. Exa meaning what? 10 to the 18. 10 to the lots. Good answer. Move that. 10 to the lots. 10 to the 18. So if you're talking about floating point operations per second, flops, we're doing 10 to the 18 flops. 10 to the 18 bytes of data being generated. That's what we mean by exascale and lots. So we'll show you what that means in a minute. This will be hundreds of thousands to millions of processors working together on one problem on the order of a week. So that's what we mean by extreme computing, just so that we can set the scale. And when we're going to get to predictive science, doing prediction of this, and so that we can deploy a new technology. And we're going to do that at a range of scales. Let me get over that faster. So why exascale? What do you mean? Why do we need that big a computer? Well, what this system is, oh, let me see. Just a minute. I want to tell you, no. I'm going to change my presentation. So hang tight with me. I want to talk to you a little bit about why oxy-combustion. I'm afraid that there's not as much combustion going on at BYU as there used to be, and that I want to fix that problem. So I want to talk a little bit about oxy. So let me find, just bear with me for just a moment.
Where's the picture from?
Where's that picture from? I'm a Canadian. Anybody that knows me knows I'm a Canadian. I have a cottage in Waterton Park where I was born and raised, and that's just north of Glacier National Park in Canada, and that's where I was born and raised and have a cottage. Those are real mountains.
You know where Pincher Creek is?
You're from Pincher Creek?
My wife is.
Wow. That's where I do all my grocery shopping, at Walmart in Pincher Creek.
That's a great place.
It's a great place.
Dentist
What's
out
your
there
wife's
by
maiden name?
Steve.
Excuse me?
Steve.
Steve? Ah. I'm related to a bunch of Steves.
Wow. That's getting more exciting.
Yeah, I should pull out my, we should skip this discussion and go to my family group sheet. Okay, sorry about that. We need cheap, clean energy in this world. Smalley was a Nobel laureate who went around the world before he died promoting the idea that of the top 10 problems in the world, he identified 10 problems in the world that were the big problems. World hunger, you get the picture. Clean water, you understand, you can list the top 10, you can think of them. And he, in these top 10, he noted that we can solve 9 of the top 10 problems if we could have cheaper energy. We know how to desalinate water. We've got the technology to do that. It's just expensive. We know how to transport it down pipelines to different places. We can solve the water problem if we just had cheaper energy. It's the cost of energy that forbids us from being able to make this happen economically. Food is really just a distribution problem, which is an energy problem. If we could have cheap energy, we could solve most of the world's problems. We need cheap energy, but we also need it to be clean. For the longest time, for many decades, the cheapest source of energy has been coal for many, many times. So coal has this advantage of being cheap. Even as natural gas has been coming down because of these shale plays, of these tight gases that have been coming on in the United States. In fact, coal is still cheaper. Even now, even right now, the price of coal compared to the price of natural gas is still nearly half the price of natural gas. Coal has been a long-term stable source of inexpensive energy. We've got to keep it low cost. But of course the flip side of all of this is the emissions. And of course in today's world it's all about CO2 and CO2 emissions. And so over that same time period, the sources of these emissions have always been petroleum. This is of course because of automobile emissions. This is the source of transportation that is by far the largest source of CO2. This is a US chart. But coal comes in underneath that as the next source. And of course, coal is a stationary source, so we can get at that. Natural gas coming in just slightly underneath that. It's dropped off in recent years because of the conversion to a lot of natural gas instead of coal. But this has dipped up again. Just this year, this last year, there have been 4 new coal plants come online, and so coal is still an issue. But of course, this last fall, the EPA announced their regulations for new coal plants, and that regulation says that all when it goes into effect, this is just the announcement of the plan that they expect to execute, that in so doing, then the new plan says that new coal plants can emit 1,100 pounds of CO2 per megawatt hour. That number, just to put that in perspective, is so each coal plant is a little different, and each natural gas is a little different, but roughly that's the amount of CO2 emitted if you were burning natural gas. So to make coal on a par with natural gas. So so how many people are doing research on coal? Thank you. Thank you. And okay, a few of you. So do the rest of you even know how most of your power, this deriving all of these lights, is coming from coal? Do you know the process by which you're getting that power is in a large unit, a large boiler, that is taking coal as mined in large chunks, pulverizing it in mills, in ball mills, right at the facility. These are those mills. Those have been entrained with air into the boiler. Now, just for scale, you can see that's the size of a man, an individual, a person, a human being. So you can put a scale on this whole thing. This is a boiler by Alstom, as you can imagine, because that's what we're working with, who fires all of their boilers in the corners that looks like this. So the air is entrained into injectors at these coal nozzles with air coming in around the outside of it. The pulverized coal itself looks like about black face powder. The guys, the people who've been working on it out back can bring it in on their feet, and it's just black face powder all over. And then it's fired into this fireball in the middle and burns. That heat is radiated to the water in the walls. That water is turning to steam and in these superheater sections that are hanging down, and that superheated steam then goes to turn a turbine that makes the electricity that lights our lights. Now, if we're going to get the CO2 out of this, of course CO2 is a product of that combustion process. If we're taking, that's the energy we're using, is these carbon bonds, that we're taking energy out of those chemical bonds to then convert them to electric power. And if we want to take that CO2 and capture it and use it somehow, then we've got to separate it from the flue gas that's coming out the stack in those systems. If you're looking at pulverized coal, there's about a composition of a pulverized coal flue gas. But if you're looking at natural gas, that's the composition. So you can see the difference in the CO2 content. So it's the driving force is easier for pulverized coal, but there's certainly more of it. So this is the issue in this. And if you want to compare that to how much is in air, of course, this is the big deal. These 400 parts per million that's in our background air, that is a greenhouse gas. So we need to separate that out. That separation process we also know how to do, and there's a number of different systems to do the separation. In fact, Praxair, where's my Praxair guy? He's here today, isn't he? He didn't come.
Air Liquide.
Air Liquide, ooh. He is here. I'm sorry for accusing you all of being your competitor. I apologize. They have processes that they can do this process for you, and but it's not cheap. So if they won't tell you the price, I will. So here is, and it's changing. The technology is changing and the price is coming down. So if you look at a pulverized coal separation unit or a post-combustion cleanup, in 2010, here was the prices. In 2012, here's the prices. If you look at natural gas, of course, with its driving force being lower, then it changes between 2010 and 2012. You see what those are. Now you measure this in different units. You can think about it in the incremental cost of electricity. So how much does it cost more if you were going to separate this out to your electricity bill? That's how much more it would cost. 3 cents per kilowatt hour. Or you can think of it as energy penalty. How much extra energy do you have to generate to pay for the separation cost? And there it is in percentage. And then the mitigation costs, then if you just want to talk about tons of dollars per ton of CO2 avoided, how much CO2 you captured, then there it is in dollars. So That's not cheap, especially when you compare it to the price of transportation and storage. So if you took that CO2 then and put it in a pipeline and took it someplace where you could use it for tertiary oil recovery or to store it in a formation, a geological formation in the ground, both of those, the transportation and the storage, cost about $15 per ton of CO2. So the separation cost is much higher. Now, and you have a group of people working on other separation processes to try to bring this price down. Professor Baxter and his team of people, and I don't know what he's quoting for his technology, but he can tell you that at another time. This is, and that must have been Praxair's prices. I have no idea if they're Air Liquide's prices. One technology that is thought to be less expensive is oxy-combustion. So instead of doing the separation of the CO2 from the flue gas, separate out the oxygen from the air and use pure oxygen as the combustion source in the boiler. So then you realize you don't have this nitrogen to deal with in the flue gas, because the products of combustion here are CO2 and steam, water, and then the other criteria pollutants that might be coming out of such a system. And then to make it look more like air, you recycle some of that CO2 and mix it with the oxygen, so you're burning with a mixture of CO2 and oxygen instead of nitrogen and oxygen, which comes from the air. That's the process that we're working with Alstom on designing. Okay?
Is that because pure oxygen would be too hot?
That is correct, potentially. That's because pure oxygen is going to be a very different combustion system than existing systems. And most engineering systems are anxious to do incremental changes, not extreme changes. And so there's a lot of work of pushing towards pure oxygen, but those kinds of systems are going to look very, very different than systems with diluents in them, with inerts in them. So this makes it look at least closer. It's going to be different already than air, and but at least we've got systems that we can kind of understand that are somewhat like it. Okay? Okay. Now why is, so you can see that this is a large-scale computation immediately. And instead of going through all of the issues of dealing with all of these particles, I want to talk about just a few of those in the next few slides. I want to show you a simulation that we've done already. So this is 10 seconds of real time. You're looking at the oxygen concentration in that boiler. This was done with large eddy simulations on 6,000 cores. So this is on a petascale machine, not an exascale machine. And so 6,000 cores used simultaneously for about a week and a half to get this simulation of 10 seconds of real time. And the resolution in the system, for that one that you're looking at right there, is 2 centimeters. So you saw the size of the boiler, and the resolution of the finest scale that we're resolving is 2 centimeters on the side. It's a cube. And then you can see what's happening with the ejection and the kind of things that's going on. Once we get to exascale, which is our objective with the new project, we will be moving from 2 centimeters, or 1 centimeter resolution, down to a millimeter resolution. So we're using time scales now on the order of 10 to the minus 6, and we'll go to about 10 to the minus 8 in time scales on exascale, and we'll be down to about a millisecond. And right now we're doing a millisecond. So we're moving to a millimeter and 2 orders of magnitude down in time scale. Okay, now I'm going to switch back to that other presentation. Any comments so far? Questions while I just make another shift for you, please?
Well, you're shifting. So that's tremendously expensive to compute at that scale. What are the advantages that you get at that scale that you wouldn't have if you did just a petascale?
You are my straight man, Bill. Let me actually do that very next, that slide next.
I said it with a straight face.
You did say it with a straight face, and but it's back in the other presentation. So this, let me show you this slide. So a state-of-the-art simulation with existing technology would be shown on the left. This is a slice near where those burners were coming in from the corners. You're looking at oxygen concentration just like you were looking in that dynamic simulation that I gave you. Horizontal slice. Thank you, thank you, thank you. Keep me honest. So so this is what we're firing from the corners, And this is a Reynolds average Navier-Stokes simulation, so it's an average computation over how this thing is changing dynamically. You can see all the turbulence going on. There's where the oxygen concentrations are sitting in that system. This computation was done by our partner Alstom, and those dots that are on there are their measurements. They've stuck probes in and measured local temperatures, and so the color represents the local measured temperatures in that furnace by Alstom. And then there's the simulation.
How big is that furnace?
That furnace is, in dimensions,
Is that under a pilot scale?
this is the BSF where they've got the data, that's correct. So this is a 15 megawatt system right now. I showed you the picture of it at the very first slide that I showed you, which was about 4 stories tall, about 8 meters on a side, something like that. Okay? Okay, so that's the simulation, those are the measurements, and maybe that says the story. Here is a resolution at 1 centimeter resolution on Titan. This was done on 8,000 cores at one time slice, so you realize that this will move around in average. So a picture's worth 1,000 words. I'm going to show you by the time, within the next 7 minutes, then I'm going to show you comparisons of what we mean. We're moving towards formal validation and uncertainty quantification. So a lot of simulation work in my lifetime, in moving from here to where I am now, to the gray hair, we have seen simulation science be now stated all over the place as a third branch of science. So in my lifetime, in my history, in this room, we've created a new branch of science, simulation science. And that's building on, and you've probably heard that yourselves, you know, this measurement science and theoretical science, and now simulation science. And that simulation science is a young discipline, truly is learning about how to do the science of simulation. And particularly this aspect of validation, which links the simulation with the experiment and with the theory, and makes them all work together. And it's the validation process that makes that occur. And our validation up until now has been very, very subjective, not very scientific and not quantitative. This has been the way we do validation. So whether it's here with these colors, see, there's what we predict, there's what we measure. How good is that? You decide. That's your subjective decision. Or whether we put it on an XY plot and put the same numbers on there and say, now we're quantitative, we've got numbers. Here's the simulation line. Here's the measurement. How good is that? And then you still decide subjectively. We're trying to move now in this discipline to more very formal processes of validation and uncertainty quantification, so that we can quantify the information gain or the information lost and talk about what that means. And I want to show you that exactly in a moment. And the answer, exactly in a moment. So, and the point being that, does this resolution matter to us? And can we quantify how much that resolution matters to us? And why do we need it? There'd been a lot of thought that because of this, because of that comparison, that wasn't good enough for the quantities of interest that we're interested in. And so we need more information somehow, more science that we can bring to the table. And not only more resolution, but we can deal with more science. This isn't just all about resolution. We're not using the same models. Here we have to average and make approximations in all of the components that are going in. Here we can draw more on the fundamental science that gets tied to the system and put it all together. So the hope is that more science will give us more information that will have an impact on society. That's the hope. We're at BYU, we have hope and faith. And so that's the hope and faith. And now we'd like to quantify that scientifically. And let me move in and just show you just briefly. In fact, I've spent too much time on this one example. So let me show you that with respect to the science, with one aspect of the science, and then I want to show you a comparison on the data. And then we'll move on to the next example. Okay, so I'm assuming everybody is, who's teaching your graduate transport class? Whoa, he's on, the exam's on, he's on now. How much turbulence do you cover in?
About 1 day.
About 1 day. So do we do an energy spectrum?
No.
Okay. Okay, so shame on you! So when we think of turbulence, you realize that we have, you all know enough about turbulence to realize we have this cascade of eddies from large to small. So I'm looking at a turbulent system at any one point in a system. As time goes by, I see eddies of all sizes go by me at that particular location. So we like to quantify this process by thinking of this energy spectrum. And this is a power spectrum that you probably do if you've done in your electrical engineering classes or otherwise. But we like to think of the kinetic energy of those eddies and recognize that there's a hierarchy of eddies, and that they're dissipating that energy because they're at this hierarchy of eddies. So I'm sure that you learned. I'm positive that you learned that in fact this momentum balance is. It's just an energy balance that's going on here. And as much energy is put in the system, we have to dissipate it in the system. And that's why we create these turbulence so that energy can be dissipated, so that we can so we can have an energy balance in this overall system. So we measure how much energy there is in each of these eddies as a function of their wave number. And you can think of this wave number as just the inverse of their size. So the small eddies are out here at this end, the large eddies are at this end. So the large eddies, at their fluctuations, are dissipating a lot of that energy. And the smaller eddies, which are a lot of the small eddies, but they're dissipating small amounts of that energy. Okay, so that's our turbulent energy spectrum. Now, if you think of throwing particles out into that group of turbulent eddies, those particles are going to move around because of their drag with the fluid around them. But you realize that if you threw in a bowling ball through those eddies, the eddies aren't going to be able to affect the bowling ball at all. So they'll be ballistic and move through all of those eddies. So if I have a particle of any given size, if I think of one of those coal particles in that particular system, just think of yourself as one coal particle. Pick the size you want to be. It doesn't matter what it is. If the eddies are small enough, and there's lots of those small eddies, then that particle is ballistic with respect to those eddies. It'll just shoot through those eddies. It doesn't know that they're there or not. But then if the eddies get large enough, there's so much energy in those eddies, that then they can pick up that particle and move them around and throw it around. And that particle will be moving right with the flow field. It's be moving with the same velocity that the flow field is moving. So they become tracers for the fluid at that point, and you use this for LDV and other kinds of measurements, is to have it follow where the particles are. But when the Stokes number is 1, so that's when the response time of the particles and the response time of the fluid are commensurate, they're about the same time scale, then you get very interesting effects. So anything near where the Stokes number is 1, so there is some set of eddies in that system where that particle is going to have a Stokes number near 1. There's a bunch of eddies where those particles are just going to be following the fluid, and there's a bunch of eddies that's going to be shooting through. But there are some eddies for that particle where things are very interesting, and it moves different than the fluid, has different velocities, and has a very interesting behavior in this particular region. That gives rise to this particular behavior. And so here's an image in a coal flame of where the particles are going. So particles of different sizes then respond to different eddies of different sizes, and they move with those eddies differently. So as a result, what happens is as you move through this turbulent flow field, the particles self-segregate, and the big particles move into one different location and along different eddies, different than the small ones do, and you get this clustering effect. And this clustering and self-segregation is critical to the combustion process because, of course, these particles are the fuel. That's where the fuel is coming from. They're the ones that are radiating and giving the heat that is changing into the walls. And so where those particles are is critical to the overall process. You're not getting the... And so the question is, how much of this behavior, this clustering, how much of the eddies do we have to resolve to understand where the particles really are? And that's the question we'd like to ask. And it's very different in an average computation than when you're resolving more and more and more of these eddies. So we can compute those in a large eddy simulation. So here's the real system. Here's my energy spectrum that I just talked about. We can resolve for a certain size machine. There are certain eddies that we can resolve. So depending on the size of the machine, you have this cutoff. It's called the Nyquist limit or the LES cutoff. And everything to the left of this, so all of these eddies that are larger than this cutoff, we can resolve fully. We compute what those eddies look like. Everything smaller than that, we have to model and approximate. And we can't get them all until we get, even exascale is not big enough to give us all of them. And then there is this mapping, find where the eddy size is, that we have a Stokes number of 1, and find out where that is relative to the size of the eddies we're resolving. So in a cold system, on the computers that we're running on right now, This is a 70 micron particle. We are fully resolving where those particles are going. We can compute where they're at. And that is at one time slice. That's the concentration of the particles in that boiler at that particular time slice. Now, if we go to smaller particles, so here's 25 micron particles. There's its mapping of its wave number, its eddy size to its Stokes number. It's sitting with a Stokes number of 1, and we're still resolving all of that. We're resolving everything to the left here. And there, at the very same time slice, is where the small particles are. So the last one showed you where the large ones are. So you get this segregation process. The little ones are the ones that end up creating the ignition processes that are occurring in the system. The big ones go on for longer and are radiating to different locations. Where these particles are is a big deal. So in that computation, here's where the 70 micron particles are in the entire boiler through a volume rendered image at one point, and there's the small particles in those systems. There's the information we're resolving. All of that translates to heat transfer, so we can get the heat flux. Same stories go with every piece of physics that goes into the simulation. What about the radiative heat transfer? How does the radiation occur? The coal particles, their soot, their concentration of the gas phase species that are also radiating. And finding out what the radiation is like in this entire system. Okay, so, boy, I keep moving back and forth between these two presentations. I didn't do very well at giving you the presentation I wanted to. So now I want to say just something that I promised about what we mean by validation. So, first, a statement on what we mean by this process of validation. A concept of validation is very much an engineering concept. There's been a lot of uncertainty quantification going on in the statistics community for quite some time. For many decades, we've been learning about uncertainty quantification. And these have been formal methods that have been mostly used historically for parameter estimation, so that we understand the uncertainty in these parameters. And these are Bayesian methods. Bayes' law is paramount in this. Bayes' law has made so much of an impact over the last 20 years. So if you haven't had a chance to really touch base with Bayes' law, is a valuable piece of information that you can carry with you for lots of places, particularly in engineering. It's this principle. In fact, we've just been learning it. 60 years after the end of the Second World War, we didn't quite realize how close the Allies were to losing that war, and that in fact, breaking the Enigma code was the key to making that all happen. And we didn't know that until disclosure of these documents that were just released just a few years ago, since 60 years after the war. And Alan Turing used Bayes' law to crack the Enigma code. And that changed the outcome of the war. It's these Bayesian methods, this Bayesian analytics, the same method that is allowing you to use Google. That's how come I'm Feeling Lucky gives you what you want, because it can use Bayes' law to do this inference and be able to do this inverse problem. And it's these methods that have been used for uncertainty quantification for some time. We're using them here for this concept of validation. And I'd like to show you what I mean by validation with this engineering concept. What we'd like to know is when we're making a simulation, we're making a prediction from a model for some quantity of interest, some value that we're predicting, that we're computing, y, from the model as a function of a wide range of parameters, a whole bunch of parameters, a vector of parameters that this model is built upon. Then we want to compare that output, that quantity of interest, and there may be more than one quantity of interest. Y itself is probably a vector. And we want to compare it with these experimental observations that we make for that same quantity of interest. And that's YE. So this defect, this is how close they compare, we would like those to agree, the model and the experiment, to agree within the uncertainty of the experiment. We know that the experiment has uncertainty in it, and we can find ways. We've worked hard in experimental methods to understand what those uncertainties are. We'd like the model and the experiment to agree within the uncertainty of the experiment, on this upper and lower bounds. All of that within the range of uncertainty in each of the parameters in the system, and we'd like it to agree with all observations for every experiment simultaneously. Not just for the one that we're looking at, but for all quantities of interest, for all experiments that we can ever do, and simultaneously, that we've ever done, make statements about agreement. That's our consistency constraint. That's what we mean by validation. So we're not making a statement that this simulation, once this is done, we're not making a statement that this is the truth yet, I mean, talking truth is an important concept here. But we are making a very strong statement that it is consistent with this list of observations. And we can list the observations. And it's consistent within our uncertainty for that list of observations and for this set of parameters, for this set of uncertainties. That's our concept of validation and what we mean by validation with uncertainty quantification. So, I've spent too much time going between slides and having fun, so I'm going to jump through this to the very end. I wanted to walk you through this example of what I meant, but I'm not going to have time to do that. So I want to just show you the bottom line, if I can get that build up there fast enough. I will go to this one. So, if in this boiler, I have measurements of the heat flux, which is the important quantity of interest to the designer, and I have those measurements at a number of different locations through this system, and so I have it for 27, 28, I can't remember, experiments at different locations in that system. I have these measurements. Those measurements are the red bar. So I've measured locally what that heat flux is at those different locations with their uncertainties. Then with the simulation, not just one simulation, but lots of simulations, because there's a number of parameters in the simulations, each which have their uncertainties. Those parameters are not only modeling parameters, but those are experimental parameters too, what we call scenario parameters. That means we don't know the feed rate into the system exactly. There is an uncertainty in that. So the experiment was done and they claimed this is the feed rate, but they said, but I only know it within this much. Well, the simulation can only do one simulation assuming a given feed rate. So we have to look across the range of those feed rates to see what the output heat flux will be. Same with all sorts of parameters in that system. So you go through all of those parameters and measure the uncertainty that you can measure with the model, and then you get the blue bar in those systems for each of those. And then you do this Bayesian search to find out when all of these experiments are consistent with each other. But not only these experiments, but all of the other experiments that you have in your hierarchy. You search through those databases and find out this consistent set between those and this simultaneously. And then that produces the subset, which is the green bar, that is consistent with all observations simultaneously. That is what we mean by validation and uncertainty quantification. So now our output from this then is the green line. And we want to ask the question then, what do we think the heat flux is? Well, our answer is, because we have done simulations and experiments together, we believe the heat flux to be, and note my words, we believe the heat flux to be these green bars, and we actually have a distribution, because this is a statistical distribution in Monte Carlo Bayesian analysis. I'm just showing you one representation of that, of what that heat flux is, and it's that small number. And look at how much information gain we have, because that's not the measured value. The measured value is the red bar, but yet we can make statements that we believe it to be the green bar, and because we've done them all together. Because this experiment, to be consistent, because for this experiment to be consistent with that experiment, or other experiments we've performed, there's a narrower range than just the experimental uncertainty. That's the information gain. So that's our process, to quantify our uncertainty and see what information gain we have. And then we can do this, so getting to Bill's question, how do we know that we need this resolution, or can we live with just something else? We do this also with models. So we look at model uncertainty too. So if we got more sophisticated models or less sophisticated models, we see where we gain consistency and how much information gain is made by using a more sophisticated model. And we can quantify how much information gain we get by moving to the next model. And that's what we're doing. And the answer, well, I'd say more, except we don't have time. Okay, that was all to answer that question.
Another question, Ben?
Don't have time for my next question.
Okay, let me go back. I'm going to show you two more examples. I want to quit that example, and I'm going to show you two examples quick. Now I know, so I've got 6 minutes, 3 minutes for two more examples. Any comments, any questions as you go while I go back and get the other two examples for you? Please.
Just have one comment that we are at the field, we develop different technology. for the optical combustion. For the price you just list, is Praxair, we take a Praxair price from our R&D center. We develop a process for the air separation process, so we can reduce the price like 20%.
Cool.
Yeah.
20%. Professor Baxter, do you want to put a number up? We'll open it up for anybody. What we want to do, so what we're after is using simulation. All I am bringing to you today is prediction. So using simulation for whatever you want with ever-increasing computer power to be able to bring that power to bear on solving important problems to society. And so that we can make decisions, informed decisions, because together we have experimental evidence and theoretical information that we can bring to bear through simulation on what's occurring. And by using them both together, we have more information than we had by doing them separately. And now it's not just subjective. In the old day, we were doing that subjectively, saying, yeah, I think there's more information here. But now we can say exactly how much information gain we have because we've done them together. Because we've done simulation and experiment together. We can make statements about the information gain and quantify the information gain. And we can see what models we need, see what we don't need. So that's the theme. You get the picture, that's the theme. And ours is just applying it to these combustion applications, which we think are important to society. Okay, that's my message. The rest are just more fun examples. Flares are a very interesting problem in today's world. These are industrial flares that you see at refineries all the time. You have to have a flare to get, it's the sewer for the refinery. But if something happens in the refinery, you've got to get rid of all the stuff you've got somehow. And you just, the way they get rid of it is to put it up the flare and burn it all. And so if there's an upset in the plant, you've got to get rid of the feedstock, you put it up the flare and burn it. And so we all understand the importance of a good sewer. And so that's what this process is about. And right now there's a lot of regulations going on by the EPA around flaring because historically we've thought that if we just burned this stuff in the open air, we certainly burned it all up because there's lots of oxygen around. You know, we've been having bonfires for a long time. Certainly there can't be any real problem with that. But there's lots of different practices we're finding that are creating problems with the emissions from flares. So there's been a lot of work working on regulation of flares. The problem is that you really can't know exactly what's happening from your flare. You can't measure the combustion efficiency from a flare. So if you want to make a lot of money, find an instrument to measure the total combustion efficiency from a flare. There's lots of money in that right now. You can maybe get some information about it point-wise, but it's a big fire up there. If you're doing this in the laboratory, it's pretty easy. You burn everything up, and then you collect everything that comes off, you measure what comes off versus what you put in, and you can compute a combustion efficiency. Collecting everything that comes off a flare is nigh onto impossible. And there's a lot of variability what's going on in the flare. So in flares, in many cases, they inject steam in the flare, and that injection process is to create the momentum, an increased momentum, so that you get more entrainment of air into the inner circles of the flare. And that makes more mixing to make it more efficient. But they've been observing that many operators will put in too much steam, and if you put too much in, you can extinguish the flame. And so, but you can't see the flame because there's all the steam around it anyway, so nobody knows if it's really burning in there or not, and so they can extinguish the flame and have all of the raw products coming out with zero combustion efficiency, and you don't even know it. And everything from zero to, of course, various degrees of it. You can see the measurement problem being so extreme. There's been a lot of money spent on trying to take a flare and take this. I should show you the real picture instead of my simulation of it, in which this is a huge pipe this big around on a crane held up at the exit of the flare, trying to move it around as a collection probe. I mean, you've got probes. This is a probe. And these are, it's just very difficult. You can see that one sample isn't going to give you the total combustion efficiency from that flare. And so it's a big problem. LES helps us in another way. I'm not even going to get to my last example, am I? I want to show you this one. Here is a project. Another thing with these flares is instead of burning it all in one pipe, you break it up into a field of flares. So there's a huge field of flares, and you fuel up each of these flares, and then they're burning this just huge field, burning away with all of these flares. So this work that we did here was for the Gorgon field. So in Australia right now, the largest natural gas field is in Western Australia, and they're taking all of that natural gas, putting it in a plant to make liquefied natural gas, putting it on tankers and shipping it to Japan as fuel. It's the largest LNG plant in the world, and yet it's also in the place where there is the most hurricanes of any place in the world. And so they're worried that if this hurricane comes along, and particularly you understand this with respect to Japan, how these issues of weather on devices. So this is going to be my last example. The bell's going to ring. So in this particular case, they're very worried that the plant will go down, but all of that natural gas is still coming through the pipeline. So they've got to burn all of this natural gas in this field immediately. And so the question is, how do we make sure that under hurricane wind conditions, this will still stay ignited? And that's what this work was aimed at. I'd have to take more time to tell you about it. But what you can see with LES, there's some so this is the flare tip down here where the fuel is coming in. Here is the temperature field from that system. And one of the issues that you see with this large-scale computing, what has extreme computing done to us here? It's allowed us to be able to get liftoff, ignition. This is a holy grail. It's been a very tough issue to get, very difficult to get in combustion in the past. And by having bigger computers, it allows us to be able to get at those aspects of the problem. Okay, the bell rang. I'm not going to show you the last example at all. Those two examples are probably enough. I'll just kind of leave it at that. But if you'll allow an old man a few missives, I'd like to make an observation. Whoops, I don't want you to see that yet. So let me just show this one, and then I'll make that. I want to make an observation first. So, we all came here under what in fact some newspaper articles call one of the 10 best mottos of a university in the world. Enter to learn, go forth to serve. Now, I recognize, I understand official nature. The University of Utah, BYU officially declares that we don't have a motto, so that's not our motto. But it's certainly on our gates, and we certainly understand it, we advertise it. I even noticed this time when I came to the Wilkinson Center that it's on the Wilkinson Center. That it must be, maybe it's the Wilkinson Center motto if it's not the university motto. But we enter to serve, enter to learn, go forth to serve. It's great, it's great. We didn't invent it, there was a professor, a geology professor at the time of Ernest Wilkinson, when he was president, that suggested that they should put that on the gates. And Ernest Wilkinson said, this is a great idea. So this came in the late 60s when that arrived. And it had been on many other universities before then. But BYU's everybody in the world still ascribes it to BYU. LDS or not, this is a great, but it's been adopted by many other universities since then. It's a great motto. We understand what it means, and it means something to us each individually and personally. And I absolutely love it. I have my whole life. And I do think it's the right kind of thing to say. But this university was, and I want to say something else first. What do I think were the most important things that I learned from this university? And if I ask that, I think that there's maybe two things. So here I think I learned how to serve. So I think I learned how to serve. So that fits with the model. And that's what I learned, is how to serve. Here, I think I learned that. And the second thing I learned, I think I learned how to learn. And those are the things I learned. So when I put that together, and this motto, and then I put together Brigham Young, I want to read you this from Brigham Young. This comes from the diary of Brigham Young. On page 248, you can look it up. Because I don't think that Brigham Young would have used that motto. I think Brigham Young would have turned it around. It is our duty and calling as ministers of this same salvation and gospel to gather every item of truth and reject every error. Whether a truth be found with the professed infidels, or with the Universalists, or the Church of Rome, or the Methodists, or the Church of England, the Presbyterians, the Baptists, the Quakers, the Shakers, or any other of the various and numerous different sects and parties, all of whom have more or less truth, it is the business of the elders of this church, Jesus, their elder brother, being at their head, to gather up all the truths in the world pertaining to life and salvation, to the gospel we preach, to the sciences, and to philosophy, wherever it may be found in every nation, kindred, and tongue, and people, and bring it to Zion. I think Brigham Young would have said, enter to serve, go forth to learn. I think that, I hope we can do that. I have learned so much. There is so much out there to learn. And I hope that we keep learning forever. This is Joseph Smith and Brigham Young. This is unique Mormonism, this principle of eternal progression, of learning forever. And it really makes me proud to be able to say, I'm from BYU. So with that, thanks for joining me.